To celebrate the 20th anniversary of spectral inversion development, let's revisit the first attempt case history, an offshore Africa application from February 2001. We had approximately 8 to 60 Hz of usable signal bandwidth to work with. Spectral decomposition provided a good view of the morphology associated with a sheet sand deposit. While this work was being done, 2 wells had already been drilled in the area. Here's a 100 millisecond flattened target zone cross-section at one of the wells. It shows the input seismic data. Below the input data is the spectral inversion layering solution. And below that, for QC purposes, a filtered seismic model based on that layering solution. The seismic model was filtered back to the signal bandwidth that was available in the input. This was to simulate the input data. This well intersected a 6-meter sand. Sonic log information indicated a sand velocity of approximately 2750 to 2900 meters per second. Using this velocity to convert the 6-meter thickness to a two-way travel time thickness, we get approximately 4.1 to 4.4 milliseconds. Zooming into the well intersection shows that the predicted layering nicely matches the true thickness. Even though we only had 8 to 60 Hz to solve for this thin bed, and an input seismic sample rate of 4 milliseconds, we obtained an accurate thin bed prediction. Worth noting that the spectral inversion is a trace-by-trace operation. It does not guide or force the layering solution to be spatially similar across adjacent traces. So in that way, it was reassuring to see a stable thickness estimate from left to right across the well time. In this example, the true thickness is considerably below conventional or traditional tuning thickness. This would be a concern if we were to use conventional or traditional resolution techniques. But since spectral inversion incorporates a spectral balancing step, source wavelet tuning thickness is not a concern. We simply use the entire available bandwidth of signal, from 8 to 60 Hz, to predict a layering pattern that accommodates the spectral interference. With this approach, the ability to detect and resolve is dependent on the available signal bandwidth, the complexity of the layering architecture, the complexity of the impedance distribution, and signal to noise. Now here's another cross-section, this time through the second well. This well intersected the sand on the downthrown side of a fault. Here once again is the input data, the predicted spectral layering, and a seismic model derived from that layering. In this case, the target sand thickness was 22 meters, a thickness just on the resolved side of traditional tuning thickness for the given wavelet. 22 meters, in this case, corresponds to 17 to 19 milliseconds of two-way travel time. Once again, the zoomed-in view shows a good match between the actual thickness and the prediction. And once again, with this approach, no need to concern ourselves with the source wavelet tuning thickness. The fault disruption shows up nicely right next to the well. Subsequent to the characterization work, 2 additional wells were drilled. In both cases, the predicted thickness was within a meter of prognosis. The predicted layering architecture was also used at the seismic grid scale as a 3D reservoir model to investigate dynamic flow connectivity. This was an area that was not yet on production. The project team was hoping to investigate the effects of placing injectors and producers in certain locations. For the scenario shown here, the producer locations are shown in red, and the injector locations are shown in blue. The pair of displays shows a synchronized view of drainage fronts from the producer perspective on the left, and the flood fronts from the injector perspective on the right. A specific question that came up during this exercise was whether there is an injector to producer connectivity across the implied shale break. Remember that what we are looking at here is a 2D map view of a single slice extracted from a full 3D layering and flow simulation. Sure enough, in a three-dimensional sense, the flood fronts do make it across the shale boundary to the producer. This quick and simple streamlined investigation also points out that for this particular scenario of injector-producer locations, the area to the north is not being swept. The message here is not that this is the end-all be-all of reservoir modeling, but rather that this is a quick way to investigate what seismic on its own reveals in terms of connectivity, baffles, seals, bottlenecks, and paths of least resistance. The spectral inversion layering solution, at its derived scale, with no upscaling, facilitates investigations regarding seismic-derived compartmentalization and dynamic connectivity. In addition to capturing dynamic views of drainage fronts and flood fronts, such simulation experiments can provide glimpses into potential pressure solutions, journey times, flood and drainage areas, streamlines, and bottlenecks via speed volumes. You would expect the speed to be high at the well penetrations. High speed zones away from wells indicate potential bottlenecks to flow. We revisited this target zone at a later stage using a set of ABO datasets. A far offset reflectivity volume that responded to hydrocarbon-filled sand, a band-limited colored inversion volume from an incidence angle range that responded to lithology that was irrespective of fluid fill, in other words, to both hydrocarbon and brine-filled sand, and a near offset reflectivity volume that responded to harder lithologies such as the brine sands. Spectral inversion was run on each of the three cases. The layering solutions represent the reflective material sensed by each of the individual input datasets. In other words, the far offset layering corresponds to layering that is hydrocarbon filled. The lithology impedance derived layering corresponds to lithology irrespective of fluid fill. And the near offset based layering corresponds to the layering associated with the harder lithologies. Seismic models derived from the layering solutions are shown in the third row. For the far offset and near offset cases, these models are the band-limited reflectivity versions of the layering. For the lithology impedance case, the seismic model is simply a band-limited version of the layering. We then combined the three layering solutions via RGB blending: blue for the softer hydrocarbon-filled sand, green for the sand irrespective of fluid type, and red for the harder layers such as the brine-filled sand, to end up with a composite RGB display. Plan views of the blends proved more information was available than through the cross-sections alone. At the horizon plus 6 millisecond mid-sheet sand level, the transition from blue to yellow shows the spatial distribution of the hydrocarbon-water contact. One of the main takeaways here is that if you only had the far offset volume to work with, you may think that the sand body abruptly ends at the edge of the blue area, whereas in fact, the sand fairway continues towards the southwest and northeast, as indicated by the yellow color. At the horizon plus 40 milliseconds zone, that is 34 milliseconds deeper, the blue far offset volume shows a hydrocarbon-filled channel. To image the meander segments that fall in the water leg below the hydrocarbon water contact requires angles of incidence associated with the lithology volume, or the near offsets. Still deeper, at horizon plus 54 milliseconds, a hydrocarbon-bearing valley shows up in blue. To image the harder gravel-dominated rock mass associated with pebble sandstone lag deposits, irrespective of fluid fill type, required the near offset and band-limited inversion layering solutions. Spectral inversion was originally developed to facilitate reservoir modeling and seismic investigations into architecture, thickness, distribution, and connectivity. The technology continues to evolve at OGS in exciting ways, but 20 years on, the mission has remained consistent: to objectively reveal, with as little subjective guidance as possible, layering representations of the geological content that is embedded within the seismic data.